Hello, this is our video review for Chapter 7, Quantum Theory and the Electronic Structure of Atoms. Throughout the video, you'll hear all of us explain different sections of this chapter. I'm Esmeralda Dueñez, and I'll be doing section 7.1, From Classical Physics to Quantum Theory. So first of all, let's talk about Max Planck. In the 1900s, he was looking at the radiation solids emit when he discovered that atoms and molecules emit energy in quanta, unlike how it was previously believed. This was the start to quantum theory, but before we get into that, we first need to go over waves and their properties. Our book defines a wave as, quote, a vibrating disturbance by which energy is transmitted. Okay, there are several properties to waves. We have wavelength, which is represented by the lambda symbol. We also have frequency, which is represented by the Greek symbol nu. We also have amplitude, and we have speed. Now, here you can see I'll explain it a little bit better. Wavelength is the distance between identical points, or the way I like to see it is from peak to peak. And then amplitude is actually from midpoint to the top of the peak. So if you're trying to get the amplitude, you would subtract the top from the bottom and divide it by 2. Frequency, on the other hand, is the number of waves that pass through a given point per second, so the number of different waves that pass through it. Speed is wavelength times the frequency, which is the formula we have down here, if you remember our symbols. So the mu is the wavelength and the frequency, so speed is u, and that gives us our formula for speed. Moving on to electromagnetic radiation. It is the emission of energy in the form of electromagnetic waves, which travels at 3.00 times 10 to the 8 power meters per second. This number is most commonly known as the speed of light. Here we have the electromagnetic spectrum. The longer the wavelength, the lower the energy. For example, radio waves. The higher the frequency, on the other hand, the higher the energy, like gamma rays. Going back to quantum, it is the smallest quantity of energy emitted in the form of radiation. The energy of a single quantum is given by the following equation, where h equals Planck's constant, which equals 6.63 times 10 to the negative 34 joules per second, and nu equals the frequency. Let's look at an example really quickly. If a radio station transmits with a wavelength of 1.2 times 10 to the 8 meters, what is the frequency of radiation? Now remember, here we have our formula. But since we're looking for frequency, which is the one that looks like a V, we would subtract it in order to get the correct formula. Then we would put in, remember the speed of light is 3.00 times 10 to the 8th. Once we do our math, we get our answer, 2.5 times 10 to the 16 hertz. Moving on to section 7.2, the photoelectric effect. The photoelectric effect is when electrons are ejected from the surface of a metal as the metal is being exposed to their threshold frequency. In order to explain this previously unexplained phenomenon, Einstein turned to quantum theory. He proposed that light can be like a stream of particles, stating that particles of light called photons possess energy by the previously mentioned equation. If light of higher frequency is used, then not only will electrons be knocked loose, they will also acquire some kinetic energy. This event can be summarized by the following equation. Ke is for kinetic energy, while W is the work of the function. While Einstein's theory of light did explain the photoelectric effect, it also raised more questions.
Section 7.3 consists of Bohr's theory of the hydrogen atom. Bohr had the curiosity of why atoms were so stable considering the opposite charges of the protons and electrons the atom withheld. He wondered why the electrons just wouldn't collide with the nucleus and crash, due to them having different charges. An electron can only obtain certain energy levels that are fixed that are at fixed distances from the nucleus. Each atom has different levels of energy due to its number of protons in the nucleus. For the hydrogen atom, the energy levels depend on the Rydberg constant, which is this one over here, which has a value of 2.179 times 10 to the negative 18 joules. As you can see, this is a chart of the emission bright light spectrum containing all the different elements and the different lines it has. An emission spectra consists of either continuous or line spectra of the radiation emitted by substances. In order to understand the electron transitions for hydrogen atom, we must know what emission spectra means. It means either continuous or line spectra of radiation emitted by substances, and line spectra means the light emission only at specific wavelengths. Each energy group has their own category name. One of them is Lyman series, Balmer series, Paschen series, and Brackett series. As the energy decreases, the gaps decrease as well. Every element has its unique emission spectrum, and it will always be different due to its unique nucleus. Here I have an example showing how to use the Rydberg constant within the problem. Section 7.4, the dual nature of the electron, talks about how physicists wondered why energies in the hydrogen element are quantized. In 1924, a physicist called Louis Broglie reasoned that if light waves can behave like protons, then maybe particles like electrons can possess wave properties. In order to understand this, we have to know what nodes are. Nodes are the amplitude of the wave, which is 0. For example, here, there is a node at the beginning and at the end of each wave. There's a node right here and another one on this side. If there's many waves, there's going to be a node in the beginning and in the end of each wave. Some of the waves, such as standing waves, can be caused by something so simple as a guitar. These are 3 examples. Here is one with 1 wave. This has the 2 different waves, and this one has 3. The greater the frequency of the vibration, the shorter the wavelength it's going to be, and the greater the number of notes, which means right here it has only 2, right here it has 3, and so forth. The relation between the circumference of an allowed orbit, 2 pi r, and the wavelength of the electron is given by this equation right here. 2 pi r equals 8 n times wavelength. This represents the wavelength of the electron, n represents the integer, r represents the orbit radius, and r can have only certain values as n increases. De Broglie's reasoning led to the conclusion that waves can behave like particles, and particles can exhibit wavelength-like properties. De Broglie deduced the particle and wavelength properties are related to this expression. This represents the wavelength, the u represents the velocity, and the m represents the mass. Here's an example on how to use this expression in real life. Okay, first we calculate the wavelength of a particle in the following case. We are giving the mass at the speed of the particle, which is for us 150 miles per hour and 68 meters per second. Here I'm multiplying 6.63 times 10 to the negative 34 joules times seconds divided by 6 times 10 to the negative 2 kilograms times 68 meters per second. And this is what we got. For us, this is what the wavelength would be.
What's up, everybody? My name is Daniel Martinez, and for Chapter 7, I have 7.5 quantum mechanics and 7.6 quantum numbers. Let's start off with 7.5 quantum mechanics. This section starts by saying Bohr's approach didn't account for the emission spectra of atoms containing more than 1 electron, such as helium and lithium. But the biggest problem with Bohr's approach is how can the position of a wave be specified? We can't define the precise location of a wave because a wave extends into space. To describe the problem of trying to locate a subatomic particle that behaves like a wave, Werner Heisenberg formulated what is known as the Heisenberg uncertainty principle. And the equation for the Heisenberg uncertainty principle is delta x times delta p is greater than or equal to h divided by 4 pi. And delta x and delta p are represented by the uncertainties in measuring the position and momentum of the particle. Delta p is the uncertainty in the electron's momentum, and delta x is the uncertainty in the electron's position. Now let's put it into play and look at an example. The example says an electron is moving at a speed of 8.0 times 10 to the 6 meters per second. If the uncertainty in measuring the speed is 1.0% of the speed, calculate the uncertainty in the electron's position. The mass of the electron is 9.1094 times 10 to the negative 31 kilograms. The uncertainty in the electron speed is, we calculate that by multiplying the speed times the percent, which is 1% times 8.0 times 10 to the 6 meters per second. And that equals to 8.0 times 10 to the 4th meters per second. To calculate momentum, we get the mass of the electron and multiply it by the speed. So the uncertainty in the electron's momentum equals to the mass times the uncertainty in the electron's speed, which is this right here. And that's 9.1094 times 10 to the negative 31 times 8.0 times 10 to the 4th meters per second. And the answer to that is 7.3 times 10 to the negative 26 kilograms times meters per second. Now to calculate the uncertainty in the electron's position, all we have to do is put this number into the uncertainty and the electron's momentum. Now we have h divided by 4 pi times delta p. And that's 6.63 times 10 to the negative 34 joules per second divided by 4 pi times 7.3 times 10 to the negative 26 kilograms times meters per second. The answer to that is 7.2 times 10 to the negative 10 meters. And this answer is the uncertainty in the electron's position. And that's the answer to the whole example. The chapter continues by saying in 1926, the Austrian physicist Erwin Schrödinger formulated an equation that describes the behavior and energies of subatomic particles in general. The Schrödinger equation incorporates both particle behaviors, mass, represented by m, and wave function, represented by psi. This began a new era in physics and chemistry called quantum mechanics. Although quantum mechanics says we can't pinpoint an electron in an atom, the concept of electron density gives us the probability that an electron will be found in a particular region of an atom. An electron orbital can be thought of as the wave function of an electron in an atom. And that's it for section 7.5, which is quantum mechanics. Now going on with 7.6, quantum numbers. There are 3 quantum numbers that are required to describe the distribution of electrons in atoms. The first one is the principal quantum number, which is represented by n. The next one is the angular momentum quantum number, represented by the letter L. And the last is the magnetic quantum number, represented by ml. To start off, we start with the principal quantum number, which relates to the average distance of the electron from the nucleus in a particular orbital. The larger n is, the greater the average distance of an electron in the orbital from the nucleus, and therefore the larger the orbital. The angular momentum quantum number. This tells us the shape of the orbitals. The value of L depends on the value of N, which is the principal quantum number we just talked about. For a given value of N, L has a possible integral values from 0 to N minus 1. For example, if N equals to 3, the possible values of L are 0 and 3 minus 1, which is 2, so it'll be 0, 1, and 2. L has 3 possible values. The value of L is generally designated by the letters of S, P, D, and as follows. If the value of L is 0, then the name of the orbital is S. If the value of L is 1, the name of the orbital is P. If the value of L is 2, the name of the orbital is D. If the value of L is 3, the name of the orbital is F. If the value of L is 4, then the name of the orbital is G. If the value of L is 5, the name of the orbital is H. And lastly is the magnetic quantum number, which is represented by ML. The magnetic quantum number describes the orientation of the orbital in space. The value of ML depends on the value of L, just like the value of L depends on the value of N. For a certain value of L, there are 2L plus 1 integral values. For example, if L equals to 1, then there are 2 times 1 plus 1, or 3 values of ML, which are -1, 0, and 1. If L equals to 2, then there are 2 times 2 plus 1, or 5 values of ML, which are -2, -1, 0, plus 1, and plus 2.
My name is Crystal Manjarres. Today on section point 7 we would be talking about atomic orbitals. Atomic orbitals are the quantum states of the individual electrons in the electron cloud around a single atom. There's 3 types of orbitals, which are the X, the P, and the D orbitals. Each subshell, depending on the orbital, has a number of certain orbitals that it should have. For example, the S subshell has 1 orbital, the P subshell has 3 orbitals, and the D subshell has 5 orbitals, which means it's the largest one it could be. Now we would be talking about the S orbitals. Are spherical in shape but different in size, which increases as the principal quantum number increases. Here are some examples of how they would look like it in size as the number increases. These have a boundary surface diagram that encloses about 90% of the total electron density in an orbital, which means that there's 90% total electron density in an orbital. We also have the p orbitals, which p orbitals have 2 lobes on opposite of the nucleus. They also increase in size from 2 to 3p to 4p and up. If n equals to 2 and L equals to 1, we have 3 2p orbitals, which are 2px, 2py, and 2pz, which are the 3 axes. These orbitals are identical in size, shape, and energy. The only difference is in orientations according to their axes. I have some examples here. This is a 2px, which you can see the 2 lobes aligned on the x-axis. and this is the 2py, which are the two lobes on the y-axis. And we also have the 2pz, which are the two lobes along the x-axis, the z-axis. We also have the d orbitals, which are used when L equals to 2, and they are 5 values of Me. By having 5 values of Me, we have the same value of d orbitals, which would be 3dxy, 3dyz, 3dxc, and 3dx squared minus y squared, and 3dz squared. All 3D orbitals on the atom are identical in energy and have a similar shape. As you can see right here, we have the 3dx squared minus y squared. They are laying around the x and y axis. This is the 3dx squared, which are basically laying across the x axis with the circle in the middle. These are the 3dxy, which are laying on the y-axis like this. And this is a 3dxz, which are basically on the x-axis. And this is a 3dyz, which are right here too. And now that we have identified the s orbitals and the p orbitals and the d orbitals, we would go on and continue with the energy of orbitals. This refers to the energy being used to take an electron present in an orbital to infinity, or the energy being released when an electron is added to an orbital from infinity. This usually depends on the quantum number, which is n, the symmetrical quantum number, which is L, and the shell and subshell. As we have talked before, the energy levels, this right here is an example of the multi-electron atom, which only depends on N and O. As you can see, the orbitals are on different types of energy, which this represents energy. They're on different levels of energy, depending on the orbital's kind. This one right here is the single electron atom, which depends only on the quantum number, which is N. Now these are usually on the same energy level. As you can see, they're all on the same energy level. They really don't change as much as over here. Now for this one, we would give the order of orbitals, which are the multi-electron atoms, which is when s is less than 2s, and so on. As you can see here, when s is smaller than 2s, and it explains as it goes further that the more it goes further, the higher the energy level it's going to be.
Section 7.8, Electron Configuration. Electron configuration is how electrons are distributed among the atomic orbitals. Right here you can see an orbital diagram, which is we're using the hydrogen atom. It has one s and it's going up. The number on top tells the electrons in an orbital or subshell. The s tells the angular momentum quantitative number, and the 1 tells us the principal quantitative number in n. These numbers help us label an electron in an atom by giving us the n, l, me, and ms. Next, we will go ahead and move on to the Pauli's exclusion principle. This principle is used to find electron configurations. Only 2 electrons of an atom can have the same atomic orbital, but it has to have different spins. We would go ahead and move on to diamagnetic and paramagnetic. Paramagnetic substances are those that contain non-unpaired spins and are attracted by a magnet. This occurs when the same or parallel spins, which they're both going up or they're both going down, they reinforce. And diamagnetic substances do not contain are not unpaired spins and are slightly repelled by magnet. This occurs when the electron spins are parallel and anti-parallel to each other, which they are going in opposite directions.
The measurements of the magnetic properties are very useful when finding specific electrons configurations on elements. This is helpful to show us the unpaired electrons. Any atom with odd numbers of electrons will have unpaired electrons, which would be diamagnetic. The atom containing even number of electrons depend if they would have unpaired or paired electrons, which would be mainly paramagnetic. We would go ahead and go on with the shielding effect in many electrons atoms. This effect is mainly to reduce the electrostatic attraction between the protons in the nucleus and the orbitals 2s and 2p in the electron. The Hund's rule states that the most stable arrangement of electrons in subshells is the one that with the greatest number of parallel spins, which are basically the most diamagnetic. The general rules for assigning electrons to atomic orbitals: number 1, each shell or principal level of quantitative number n contains an n subshell. Each subshell of quantitative number L contains a 2L plus 1 orbitals. Number 3, no more than 2 atoms can be placed in the same orbital. And number 4, to find the maximum number of electrons in an atom is used as 2n to the second power. Section 0.9 is the building up principle. This is the classification of groups of elements in the periodic table according to their subshells filled with electrons, which have the negative charge. The noble gas core is the highest filled subshells. The transition metals have unfilled d subshells or can give cations that have incomplete d subshells. The lanticides are rare earth metals have incomplete 4f subshell can give cations that have incomplete filled 4f shells. Antacid series, they have been synthesized. The Doof principle, as protons are added one by one to the nucleus to build up the elements, electrons are similarly added to the atomic orbitals. As you can see here, group 1 and group 2a are usually on the s orbitals, and the transition metals are usually on the d orbitals. The noble gases and part of the metalloids are in the p orbitals. The helium and hydrogen are in the s orbitals, and the lanthanide and antacid series are in the f orbitals.